Back to McMaster University course, Computer Science 1JC3, Introduction to Computational Thinking. Today we're going to continue with the topic of information security. And more specifically, we're going to talk about public key encryption. So public key encryption is an ingenious idea that was discovered but kept secret by the United States NSA, the National Security Agency, and by the UK Communications Electronic Security Group in the 1960s. Later, Whitfield Diffie and Martin Hellman, they discovered and publicized this idea at Stanford University in 1976. And for this work, they both won together a Turing Award in 2015. Now, the motivation for this is, as we just saw with previously with conventional encryption, the key to conventional encryption is a key that must be kept secret. So if you're going to encrypt something and you're going to let someone else decrypt it, they need to have the key. You need to have the key, they need to have the key. So how do you share this key and keep things secret? And in today's world with the internet, if you're sitting someplace and the person you want to communicate with is on the other side of the world, how do you get your secret key to them? This is a very difficult task. So that's one problem that motivates public key encryption. The other problem is, how do you sign something digitally so arbitrary parties can verify it? So let's say I want to make a statement and I want people to know I made the statement. So the normal way is I would write the statement out, I'd put my signature, people look at it and say, yep, that's the signature, that's the right signature. But how do you do that in the electronic world? How do I sign something electronically, digitally, so that other people are sure that I'm the actual person who originated it? So these are the two problems that public key encryption are motivated by. Okay, so here's how it works. Each end system, so we're going to have two systems, A and B, they're communicating with each other. Each of them has a private key and a public key. The private key is kept secret, the public key is public. And the way encryption works is that with encryption, we have a plain text, and with the public key, we use our algorithm F to encrypt it into ciphertext. And then we can take that ciphertext and our private key and produce plain text. But we can also take the plain text with our private key and produce ciphertext. And we can take the ciphertext with the public key and produce plain text. And I'm going to go over this again a little bit slower. So the algorithm is used, the same algorithm is used for both encryption and decryption. And the important thing is it's mathematically infeasible to derive the private key from the public key. The public key is public. Presumably everyone has access to it. But if you have the public key, it's mathematically infeasible to figure out what the private key is. Okay, so let's look at these four approaches: encryption, decryption, signature writing, and signature reading. So the first one was encryption. Now, the idea with encryption is I have plain text, and I want to encrypt it in some way that we can produce ciphertext that only the person who's supposed to be able to read it can read it. So let's go back here. So I have plain text. I'm going to use a public key. So the important thing is, whose public key am I using? So we're A here. We have plain text. We want to send it to B. And so what we're going to do is I'm going to use B's public key. It's public. I can just go get it. And then with the plain text and the public key, I produce ciphertext. Now, this can be decrypted with B's private key. And then B can find the plain text. So the important thing is, I take B's public key. B may not even know me, but I take B's public key. I encrypt the plain text. I produce ciphertext. I give it to B. B takes his or her private key, which is secret, and decrypts it and gets back the plain text. So this is how encryption, going to the left, going from left to right, and decryption from right to left works. Okay, so that's doing encryption and decryption. So we also have this other way we can use the same system, signature writing and signature reading. So how does this work? So again, A has something. It could be plain text. Maybe we shouldn't even call it plain text. We just have something. And we have some piece of, I'll just say a document. And I'm going to take A's private key. And I'm going to now produce a encrypted document. Oh, maybe I should have just called it. Let me call this plain text. And we're going to produce ciphertext. So B gets this ciphertext, and if B knows it's from A, B goes and finds A's public key. And then applies the algorithm and gets the plain text. And what that tells B is that this plain text, whatever it is, it was sent from by A. Because only A, presumably, has A's private key, and B used A's public key and produced this text. So this is signature writing, going left to right, and signature reading, going from right to left. So actually this is a clever system because we can use it two ways. We can use it for encryption and for digital signature writing. Okay, so I have a question now for you. What would normally not compromise the use of public key encryption? I'll give you a moment to think about that. Okay, thank you for coming back. What would normally not compromise the use of public key encryption? Well, having public access to a private key would compromise the system. Private keys must be kept private for this to work. So I circled this. Maybe it's better. This is not the right answer. Now, public access to a public key, that's okay. This is a good, useful answer. Public keys are meant to be publicly accessible. Using someone else's private key, this can compromise the system because everyone is assuming that each person or each principal only has access to their private key. They don't have access to anyone else's private key. And the last one is pretending your public key is someone else's. If you can pretend that your public key is someone else's, if we go back to our picture. Well, actually, let's think about the first case. The first case is if you know someone's private key, like let's say C, you're C, and C knows B's private key, A could encrypt something, send it to C, thinking that they're sending it to B, but C has B's private key, and now C can find out what A sent. But A didn't send it to C, A sent it to B. So this is a problem. Another problem, which is the second one, is that A is going to send some plain text to B, and A wants to sign it, say this is from me. But if A can pretend like A's public key is, let's try to make this a little clearer. So A wants to send B plain text and wants to make B think it's from C. So what A does is it pretends like A's public key is C's public key. Then it takes the plain text, it encrypts it with A's private key, it gets to B, B thinks it's from C, B goes and gets C's public key, which isn't C's public key, it's really B's public key. They decrypt it and think, oh, this was signed by C, but it wasn't. It was signed by A. But B's confused because A has pretended that their public key is actually C's public key. Okay, so all the things I've crossed out can compromise the use of public key encryption. Okay, so what are the applications for this? Well, you can already guess. The first one is confidentiality. That's what I explained that's what I explained at this top part up here. And the second one is we can use this for integrity, digital signature, and non-repudiation. So we can use the second picture here for all three of these. So integrity means that if we sign something, then we know it's meant to be the way it was when it was signed. So this is a way of preserving integrity. We've already talked about digital signature and non-repudiation. If something is signed by A, and when B verifies the signature, B knows that it came from A. And if someone says, well, if A says, no, I didn't send it, B can just say, here's the document, I use your public key, it decrypts it. It must have come from you as long as your private key is secret. Okay, so that's, now let's see, there's one thing I wanted to mention is when I described it, we don't actually have to encrypt. Let's go back to this picture. We don't actually have to encrypt the whole plain text. It may not be that there's any need to protect what's here. We're just trying to sign it. So what we can do is produce a digest. Now a digest is just it could be like a hash of this, and we do everything with the digest, and over here we get the digest. And the digest is generated from this. We encrypt that, and then to verify the signature, we decrypt that. So a digest you can think of as a signature that is attached to the document or text. Okay, now the third application is if we want to do both of these together, which is possible. So the way this works is the sender encrypts the plain text message with its private key, and then the sender encrypts the ciphertext message with the receiver's public key. And then the receiver, who will presumably be the only one that has the receiver's private key, they decrypt the ciphertext with their private key, and then the receiver decrypts the next ciphertext message with the sender's public key. So we can combine both of these. And the last application, which is really most important, is using these techniques for secret key exchange. So I want to mention an algorithm called the RSA algorithm. This is a very famous algorithm invented by Ron Rivest, Adi Shamir, and Leonard Adelman in 1977. These three won the Turing Award in 2002, quote, for their ingenious contribution for making public key encryption useful in practice. So this is one of the oldest and still most popular public key encryption algorithms. And the interesting thing is security is based on the fact that if you have a product of two very large prime numbers, factoring that product into those two prime numbers is mathematically infeasible. So that's the basic mathematical fact that the security of this algorithm is based on. Okay, so we're going to stop here and continue next time.